While watching the online lectures, be sure to use the attached packet to take notes on. You'll find the link for the packet here at the title page for each chapter. Click on it, then print out the packet. These gray boxes in the online lectures refer to the slides and pages in the packet.
In this online lecture, we're going to talk about how to interpret IR spectra. And basically what I want to show you here is the correct direction to go when you're doing this. We're going to see if you go in a particular direction, the process is very easy. If you go in the opposite direction, it can be very hard. So let me show you what I mean by direction. Look at this problem right here. It says which molecule is responsible for the following IR spectrum. And we have these molecules, 5 of them right here in front of us. So here's the correct direction. Don't start with the IR spectrum, meaning don't run to the IR and start looking at peaks and trying to see what those peaks mean. The correct place to start to make this easier is simply start with the molecule. Here's what I mean by that. Let's start with this first molecule right here. And what you do is pick out something in this molecule that is unique. And notice what's unique to him, of course, is his double bond. He's an alkene. And then what you ask yourself is, where would a double bond peak in the IR? Well, remember, let's go back to our wave number chart here. Double bonds right here, they have a medium peak at roughly 1600 to 1680. So then we move to the IR spectrum and we look in that region right here and notice there is no peak there, which means this can't be the structure for the IR. So this is what I mean by direction. You're starting with the molecule and then going into the IR, not vice versa. Now notice what this also means. It means the second molecule can't be our molecule for this IR because he has a double bond and we should also see a peak in that range. So move to the next molecule now. What is unique about this molecule? Well, he's got that OH group right here, and let's go back to our wave number chart. OHs, they're very obvious here. They are very strong and broad and they peak roughly from 3200 to 3650. So going back here, notice that's this region right here. We definitely have a strong, broad peak. So you can't rule out this molecule. We're going to leave him here. However, you can rule out the bottom molecule here because now we know our molecule definitely has an OH. That bottom molecule doesn't have an OH. The remaining 2 do, so the remaining 2 stay. So then we look at the next molecule here and we say, what is unique about him? Well, of course, he's got this carbonyl group right here. And let's go back to our chart here. Carbonyl groups right here have a strong, very obvious peak at 1650 to 1780. And if we go back to our IR spectrum here, we'll notice there is nothing going on right there. No, definitely not a strong peak. So that rules out this molecule, which means this is the answer. This must be the molecule responsible for this spectrum. Now, again, like I said, if you go in this order from molecule to spectrum, it always will be this simple. So let's make sure you got this. Let's try another problem here. Which molecule, these right here, are responsible, again, for the IR spectrum in this case? And of course, we start with the actual molecule here. We start with this first one. We notice he's got an OH and a carbonyl group. And notice, definitely no OH broad peak here. So we can immediately rule him out. And that means we could also rule this guy out over here because he has an OH. This brings us to our second molecule right here. What's unique about him? Well, definitely he has this triple bond right here. Let's go to our wave number chart here. And where do triple bonds peak? Well, around weak to medium near 2100 to 2260. So let's go back to our IR spectrum here. That would be this region right here, and notice nothing. There's nothing going on there, so let's rule out that molecule right there. Now, that leaves us with the last 2 remaining molecules, but notice, kind of hard here, both of them technically have a carbonyl group. And notice, if we go back to our chart here, carbonyl groups peak right about here, 1650 to 1780, like we saw before, and there is definitely a peak in that region here. But notice, these last 2 molecules have those 2 same carbonyl groups. There is technically nothing else really unique about either one of these structures. Which means if this is all we knew about IR spectrum, we couldn't distinguish these two structures. However, what I want to prove through this example is that you need more than just the IR chart to get questions like this correct. My point is that you need to have experience, meaning you need to go through your textbook and try out all these IR problems, because in situations like this, experience combined with the chart is going to help you get to your answer. And as an Orgo student, you should always assume that your exam is going to be extremely hard, so you want to prepare yourself to the full here. So here's what I mean. There is something technically different about these two structures. And that difference is basically this is an aldehyde, whereas the molecule above is actually a ketone, which means that the bottom molecule has a CH bond due to that aldehyde. And remember, we saw in a previous online lecture where typically CH bonds peak. They peak right about here. And notice what's unique about this IR spectrum right here. These peaks right here actually are peaks that are responsible typically for aldehyde hydrogens. If you didn't have this experience before, then if your professor put this on an exam, you would be down to 2 answers and you wouldn't know what to pick. So that's why it's so important that you look at all the examples in your textbook and you do the practice problems. So basically, these two peaks right here means that we have an aldehyde, which means that rules out the ketone. It means our answer is that bottom structure there. He is the one responsible for this IR spectrum. So that's how we use IR spectrum. This is how we interpret the data. And of course, it helps us identify what molecule we're dealing with.